Hello. So today I'll be reviewing AS organic chemistry as fast as possible, right? I'm dividing the video into three sections. The first part deals with an introduction to isomerism and some general terms that we need to know. The second part deals with functional groups, their production, and the reactions they undergo, including reagents, and conditions. And the last part consists of mechanisms involved in AS chemistry. So I'm gonna give timestamps in the description below, so you can skip to them if you want. Right? So let's start. So an organic compound typically contains carbon, hydrogen, and it may contain other elements as well. So what is a hydrocarbon? It is a compound made up of carbon and hydrogen only. And what are isomers? Isomers are basically compounds with the same molecular formula but different structural formula or spatial arrangement of atoms. They are of two types: structural isomers and stereoisomers. So structure isomers have the same molecular formula but different structural formula. Structure isomers are of three types, right? Chain isomers, position isomers, positional, and functional group isomers. So in chain isomers, we basically juggle the position of the carbon atoms in the carbon skeleton, right? Suppose we have the 5 carbon alkane in pentane. An isomer is 2-methylbutane and another one is 2,2-dimethyl propane. So remember to give commas in between numbers, and dashes have to be placed before and after numbers. All right, that's the basic. These are the basics. So anyway, in positional isomers, it's kind of the same, but here we're juggling the functional group around. For example, the 5 carbon alcohol pentane 1-ol, then an isomer exists, pentane 2-ol and pentane 3-ol. Here the OH group is just changing positions between carbon number 1, 2 and 3. Alright. What about the last one? For the last one we have functional group isomerism. Here the functional group completely changes. They exist as pairs. For example, aldehydes are the functional group isomers of ketones. Esters are the functional group isomers of carboxylic acids, and alcohols are functional group isomers of ethers. Ethers are not in our syllabus, by the way. So, for example, propanal is the functional group isomer of propanone. Ethyl ethanoate is the functional group isomer of butanoic acid, the 4-carbon carboxylic acid, and ethanol is the functional group isomer of DME, dimethyl ether. Moving on to stereoisomers, they are compounds with the same structural formula but different arrangement of atoms in space, or different spatial arrangement of atoms. They are of two types: cis-trans or geometrical isomers, and on the other hand we have optical isomers. So for cis-trans or geometrical isomerism, we require a carbon-carbon double bond, an alkene basically, sp2 carbon, 120 degrees planar, and we need two different atoms or groups of atoms attached to each carbon atom. So for example, if two hydrogens are attached to the same carbon atom, we won't have cis-trans isomerism. It depends on, like, why do we get two different isomers? Because free rotation is not allowed, right? About the carbon-carbon double bond, that is why. So if the dipoles do cancel out, that means if the heavy groups are on opposite sides, we say that we have the trans isomer. For example, trans butene is seen on the right. And if the heavy groups are on one side and dipoles do not cancel out, right, we say that it's the cis isomer, cis butene. Now, according to our syllabus, something new has been added. It may also be present in cyclic compounds. How exactly? For example, if the heavy groups, right, if they're on the same side of the group, same side of the ring, I mean, we say that we have the cis isomer, cis-3-methylcyclopentanol. Both heavy groups are on one side of the ring. But what if the OH is above the ring and the CH3 is below the ring, as you see here in the diagram? CH3 is connected to the dotted line, which represents that it's below the ring. So if the one heavy group is above the ring and the other heavy group is below the ring, it's basically a trans isomer, okay? So for optical isomerism, we require a chiral carbon or an asymmetric carbon. It's a carbon atom attached to 4 different groups of atoms or atoms, right? And the mirror images are non-superimposable, as you can see here. You have to make sure that the images are laterally inverted. Look at how I drew the COOH, right? It's laterally inverted. Make sure the wedge-shaped diagram is fine as well. It has to be laterally inverted or you won't be getting marks, okay? We use an asterisk to denote the Chiral carbon. Okay. So each of the optical isomers are called enantiomers. This has been added to the syllabus as well, especially in A2. They rotate, like physically, they are the same. Physically, they're the same, physically and chemically. They have the same melting and boiling points. They undergo the same reactions. However, they rotate plane polarized light in opposite directions. Okay, as you've seen in Malice's law, right? The new addition to his physics. Plane polarized light only oscillates in one plane, basically. So each enantiomer basically rotates plane polarized light in different directions. For example, the one on the right may rotate it clockwise, dextrorotatory, or and the one on the left may rotate it anticlockwise, which is levorotatory, right? So if we have a mixture containing equal amounts of both enantiomers, right, it's called a racemic mixture. If we pass plane polarized light through it, it will not change its direction of oscillation, all right? And if you're asked what is an enantiomer, it's basically one of the optical isomers that are formed, okay? So now we are dealing with some general terms. Fission, for example. Fission means splitting up or breaking down. It is of two types. We have homolytic fission and heterolytic fission. So homolytic fission means equal, right? Equal, and hetero means different. So for homolytic fission, it typically occurs in nonpolar compounds like bromine, chlorine. We get free radicals, right? The covalent bond breaks, and each atom takes its own electron back, basically. Homolytic fission is a type of bond breaking in which the shared pair of electrons are equally divided between the two atoms, molecules. Free radicals are formed, right? So, what is a free radical? It is a species with one or more unpaired electrons in its outer shell. They are formed after homolytic fission. They are extremely reactive because the unpaired electron has a tendency to become paired as soon as possible. It wants the octet, right? Just like the chlorine free radical. So we usually see homolytic fission in free radical substitution. In all other mechanisms, we are going to see heterolytic fission. It typically occurs in a polar molecule. So for example, AB, it breaks down to form the A anion and the B cation, or vice versa. So you show it in that way. You see how I showed it with the blue pen, right? So that's heterolytic fission basically. A is taking both the electrons from the shared pair. And remember that the more electronegative atom becomes the anion, okay? It is a type of bond breaking where one of the atoms or molecules takes both the electrons in the shared pair. Ions are formed after heterolytic fission. Classification of reagents. Reagents are of two types in organic chemistry. They are electrophiles or nucleophiles. So electrophiles means something that loves another electron. So something that loves something negative, right? Something that loves negative particles. So it has to be positive, right? So electrophiles are positive in nature. On the other hand, nucleophiles are nucleus loving, things that love the nucleus. So if you want to love the nucleus which contains protons, you need to be negative. So I typically remember it this way, like negative has an N, right? Negative has an N. So nucleophiles also have an N. That's how I remember. Like it's faster to remember. So next, moving on, an atom molecule can be a nucleophile, electrophile without being charged. Okay. For example, water and ammonia, they are nucleophiles because they have lone pairs. Okay. Or an alkene can be a nucleophile because it has an electron-rich pi bond, right? So the curly arrow must be from the nucleophile to electrophile. Remember, the electrophile can attack the nucleophile, as we've seen in A2 chemistry, where the nitronium ion attacks the benzene ring, for example. You're going to learn this next year. Like the attack can be from the electrophile to the nucleophile. However, the arrow has to be drawn from the nucleophile to the electrophile, and the arrow must be curly. The curly arrow represents transfer of electrons. So next we need to know what a carbocation is. It's an organic compound with a positively charged carbon atom. It is of three types. Why are carbocations formed so easily? Typically because carbon is on comparatively it's on the left hand side of the periodic table, so it has low electronegativity. So the other compounds except hydrogen which are attached to it have a tendency to take away its electron. So carbocations are of four types: the methyl carbocation, primary, secondary, and tertiary carbocations. Down this group, right, stability increases. Why is that? Because alkyl groups have a positive inductive effect. What does that mean? They have a tendency to donate electrons. So think about it. A carbocation is positive in nature. It wants to react with something that is negative, right? So if other groups donate electrons towards it, the intensity of the positive charge on the carbocation will actually decrease, making it a weaker electrophile, right? So on the other hand, a primary carbocation, it only has one alkyl group, so the intensity of the positive charge is not reduced that much, right? Comparatively. We say that electron releasing groups have positive inductive effect. Alkyl groups are electron releasing positive inductive effect. Okay. Why is a tertiary carbocation the most stable? It has three alkyl groups attached to the carbon atom. Alkyl groups have positive inductive effect, so they stabilize the positive charge on the carbon atom, which means reducing the intensity of the positive charge. So you need to know this. This is the relative stability of carbocations. Okay, now we're moving on to the second section of the video, where I'm talking about alkanes, all the functional groups, their reactions, how we produce them. So try to connect the dots. Okay, so to produce alkanes we have two routes. This is directly taken from the syllabus. Okay, hopefully I haven't missed anything. If I did, please let me know. So we can produce alkanes from alkenes, right, by an addition reaction which is called hydrogenation using a nickel or platinum catalyst, plus we also require heat. Okay, so we also require heat, and we're going to get an alkane. There's another route. We can use alumina catalyst along with heat for cracking. We break down bigger hydrocarbons to form smaller ones. We get an alkane and an alkene, and this is done to produce more economically favorable smaller alkanes and alkenes, which are more useful for us, right? They have a few reactions. They can undergo combustion, which is of two types, complete and incomplete. In complete combustion, we get carbon dioxide and water. You can balance this, it's pretty simple. And in incomplete combustion, due to lack of oxygen, we can either get carbon monoxide, which is a harmful gas, it binds to hemoglobin irreversibly, or we can get soot, just carbon, when we have very less oxygen present. Okay, what is the other reaction of alkanes? Free radical substitution. Basically alkanes react with bromine or chlorine in the presence of UV light, and basically chlorine substitutes one hydrogen in the alkane, and this is a chain reaction. It keeps on occurring until all hydrogens have been removed. I've discussed the mechanism at the end of the video. Okay, so alkenes, all alkenes are sp3 carbons, by the way, 109.5 degrees and tetrahedral in shape. All alkenes are sp2 carbons. They are 120 degrees bond angle, and the shape is trigonal planar. So to produce alkenes we have multiple routes. We can either dehydrate an alcohol using aluminium oxide and heat, alumina, pumice, or concentrate H2SO4 plus heat, or concentrate H3PO4 plus heat. In some mark schemes they show heat with H3PO4, sometimes they don't. You can also crack alkanes, right? We saw that beforehand, using alumina plus heat. And we can also eliminate halogenoalkanes using ethanolic NaOH, okay, along with heat to get alkenes. That's an elimination reaction. These are the three routes. So what are the reactions? Mainly they undergo electrophilic addition. You will classify all of these as addition reactions. Okay, in the mark scheme sometimes they don't accept hydrogenation. It's an informal term. So even though it's in the syllabus, right? So the first reaction is hydrogenation. This is also addition. We add hydrogen gas with the help of nickel or platinum catalyst and heat to get alkanes. We can add water in the form of steam in the presence of heat and H3PO4 catalyst, right, to get alcohols. They also react with hydrogen halides, HX, gaseous form in room temperature, right, under these conditions to form halogenoalkanes. No heat is required. They also react with chlorine and bromine and halogens in general. No heat is required as well. This occurs at room temperature to get a dibromo or a dichloro compound. All right. This is also the test for unsaturation, because we know that when bromine is added to alkenes, it gets decolorized, right? So these are the electrophilic addition reactions. I want to talk about something else, Markovnikov addition. What does this state? Like in this alkene over here, propene, if we add HBr to the compound, we have two routes. Basically, we can either get one bromopropane or two bromopropane. However, we see that Right. So in Markovnikov addition, we have two possible routes. Either from propene, we can get one bromopropane or two bromopropane. But two bromopropane is the major product at around 70 to 80%. Why is that? Because the intermediates produced during the electrophilic addition mechanism are the one above and below respectively. So the one produced above for 1 bromopropane is a primary carbocation and the one below is a secondary carbocation, which has more inductive effect, positive inductive effect, due to the presence of two methyl groups. That is why it's more stable. That's why we get that in a higher quantity. Okay. So the next reaction is oxidation. It can be done in two ways. We can either use cold dilute KMNO4, acidified cold dilute KMNO4 with alkanes to get diols, or we can use hot concentrated KMNO4, which is acidified as well. This causes oxidative cleavage or rupture of the alkene. So there are three possibilities. If there are two alkyl groups attached, look at these hands, right? These are the alkyl groups. If there are two alkyl groups attached to the carbon, we're going to get ketones. Okay. If there is one alkyl group, we're going to get carboxylic acids. Look, there's only one hand over here, regardless of the length of the chain, right? If there's one alkyl group, we're going to get carboxylic acids. What if there are zero alkyl groups? So, for example, in ethene, we basically get methanoic acid first, which is unstable in the presence of KMNO4, right? So further oxidative cleavage occurs. You're going to see this in Edu chemistry a lot though, not in AS. So we get carbon dioxide and water afterwards, okay? So I would just want to say something. There are two acids which are unstable in the presence of KMNO4, methanoic acid and ethane dioic acid. These further oxidize to form carbon dioxide and water. Okay, so these are the smallest carbon containing products. All right. So what is the last reaction of alkenes? They undergo addition polymerization. For example, ethene can undergo polymerization to form polyethene. I'm showing you the repeat unit. You have to show dangling bonds in the case of repeat units. Okay. Next, we have halogenoalkanes. We can produce them mainly by free radical substitution of alkenes in the presence of UV light with chlorine or bromine. We can add hydrogen halides to alkenes in room temperature, at room temperature. Okay, so there are multiple ways we can produce them using alcohols. We can use PCl5 at room temperature. We're going to get the halogenoalkane. More on this later. We can use PCl3 along with heat to get the halogenoalkane. We can use thionyl chloride to get the halogenoalkane. This also occurs at room temperature. We can use a hydrogen halide. We heat or heat under reflux. Okay. In this preparation is in situ, inside the reaction vessel basically, or we can use halide salt like KBr and a concentrated acid like H2SO4 or H3PO4. This is also in situ preparation. We need heat under reflux. Basically, this is under the halogens chapter. KBr first reacts with H2SO4 to form HBr, the hydrogen halide. Then the hydrogen halide reacts with the alcohol to form the halogenoalkane. Why do we do it in this way? Because the hydrogen halide is typically gaseous, right? So it's very difficult to make it react directly with the alcohol. So we need this in situ preparation, okay? Heat under reflux. Okay. What reactions do they undergo? Nucleophilic substitution mainly. This is the characteristic reaction of halogenoalkanes. Three nucleophilic substitution reactions are very important, but before that, remember that there are two types of nucleophilic substitution. 3-degree halogenoalkanes undergo SN1, while 1-degree halogenoalkanes undergo SN2 nucleophilic substitution reactions. 2-degree can take part in both. So if you're given a question with a 2-degree halogenoalkane, if you draw either one, you're going to get full marks, okay? It's fine. So the three nucleophilic substitution reactions are, the first one is with NaOH aqueous. It does react with water also, but it requires a lot of heat. It's going to be a very slow reaction. In the presence of NaOH aqueous, it's going to be a very fast reaction. This reaction is classified as hydrolysis. The hydroxide basically replaces the chloride in the halogenoalkane. We get an alcohol. We can also react it with ethanolic ammonia, and we have to apply heat in a sealed tube or heat under pressure. That's what you need to write to get marks. We're going to get the amine. So here's the thing. This is a pretty hard one. You need to understand that the amine can also act as a nucleophile. Why? Because it has a lone pair. I haven't seen this in AS yet, but it was in the March-Feb 2022 paper for A2. Basically, it can act as a nucleophile again because it has a lone pair. So it can react with the halogenoalkane again if it's in the same container. So the reaction will keep on occurring until the nitrogen runs out of hydrogens, okay, to replace the chlorine or bromine in the halogen alkane. Okay, it's a chain reaction, kind of like free radical substitution. What's the last nucleophilic substitution? The halogen alkane can react with KCN, ethanolic KCN, in the presence of heat to form nitriles. Okay, so there is another reaction though. This was mentioned in the syllabus. Silver nitrate, ethanolic silver nitrate can be reacted with the halogen alkane to actually figure out which halogen was present in the alkane, right? So if we get a white precipitate, it's going to be silver chloride. If it's cream, it's silver bromide, and if it's yellow, it's silver iodide. And it's important to mention that the silver iodide, I mean the yellow precipitate, will appear the fastest. Why? Because the CX, the CI bond is the longest, right? It's the weakest, and there's minimum orbital overlapping. Sorry. So what's the next reaction? Halogenoalkanes also undergo elimination in the presence of ethanolic NaOH. We get alkenes. All right. This is very important. We get alkenes. So the inorganic products are actually so HCl is removed from the halogen alkane, right? So it actually reacts with NaOH afterwards to form NaCl, right, plus H2O. These are the inorganic products. Be careful, okay? So this follows the Sizer rule, which states that if there are two possible elimination products, we'll get the major product as the one which has more alkyl groups. So for example, we had 2-chloropropane, right? So the major product will actually be but2-ene rather than but1-ene because it has more alkyl groups. It forms a more stable intermediate. Moving on to alcohols, we can produce alcohols by hydration of alkenes, steam plus H3PO4 catalyst, oxidation of alkenes using cold dilute KMnO4, right, diols, hydrolysis of halogen alkenes using NaOH aqueous plus heat. Okay, and also we can reduce aldehydes and ketones using both LiAlH4 and NABH4. Both work, although LiAlH4 is much stronger. These are the reduction equations using nascent hydrogen. Okay, so you can use this nascent hydrogen to show these. These come quite often. So you will only give a water on the right hand side if necessary. For example, I did not require water to balance the equation, so I did not give water on the right hand side. Okay. We can also reduce carboxylic acids using LiLH4 only to get the primary alcohol. Okay. So aldehydes give us primary alcohols, ketones give us secondary alcohols. What about the hydrolysis of esters? They also give us alcohols. This can be done in two ways, either acidic hydrolysis or alkaline hydrolysis in the presence of heat. We're going to get the alcohol. Here I broke down ethyl ethanoate to form ethanol. What reactions do alcohols undergo? They will also undergo combustion to form carbon dioxide and water. They react with active metals to form alkoxides. For example, ethanol reacts with sodium to form sodium ethoxide. Why? The alcohol is slightly acidic. What about this? They also undergo nucleophilic substitution. Now I'm going to talk about these in details. It reacts with PCl5 and SOCl2 at room temperature to form the halogen alkane. For PCl5, it will produce phosphoryl chloride, POCl3, and steamy fumes of HCl will be seen. It will react with PCl3 in the presence of heat to form phosphorus acid. It will also react with SOCl2 at room temperature to form SO2 and HCl. This is the best way to prepare the halogen alkane. You'll find this in MCQs often because all the other products are gaseous, so they will leave the container. You'll only end up with the halogen alkane. So I've missed two reactions here actually. So PCl3 is quite stable, but PBr3 and PI3 are not that stable. So if you want to get the bromoalkane or the iodoalkane, you can opt to go for PBr3 and PI3, but they need to be made in situ. They need to be made in situ. For example, we can use red phosphorus, which is literally red in color. It's not hot. Red phosphorus and bromine, right? You can use these to make PBr3 in situ. Then this can react with our alcohol CH3 CH2OH to form CH3 CH2Br, right? So this is one way of preparing um, halogen bromides or iodides. Okay, I mean bromoalkanes basically. They also react with HX in the presence of heat under reflux, and you know the in situ preparation KBr plus H2SO4 to form HX, and then following the reaction with alcohols to form halogenoalkanes. This has to be done in situ because HX is very unstable and it's very hard to react directly. So we need to make it beforehand inside the vessel because the reaction temperature is too high, right? It needs heat, so the gaseous product would escape. So we need to make it inside the container and then react it. Okay. Typically, we heat under reflux when the temperature at which the reaction occurs is higher than the boiling points of any one of the reagents. Okay. So we can also oxidize alcohols using K2Cr2O7, acidified K2Cr2O7, which is preferred, or KMnO4, acidified. Primary alcohols are oxidized to carboxylic acids if they are heated under reflux for a long time, for some time actually. They can also be oxidized to aldehydes. Basically, the route is like this: primary alcohols are oxidized to aldehydes followed by carboxy acids. So you can get the aldehyde if you heat it and distill it almost immediately. So distillation needs to take place almost immediately. So secondary alcohols are oxidized to form ketones. I've shown you the reactions. So here I'm using nascent oxygen, but like I'm using water, right? Or else the equation wouldn't have been balanced. That's why I need to use the H2 on the right hand side. Okay, so tertiary alcohols cannot be oxidized. You'll frequently get trick questions. Okay, remember that. Got it? So they also undergo dehydration. We have three routes for dehydration: alumina plus heat, concentrated H2SO4 plus heat, and concentrated H3PO4. You will see that this one does not require heat, okay, for dehydration. We will get one molecule of water afterwards. So for esterification, alcohols react with carboxylic acids in the presence of a few drops of concentrated H2SO4 and heat under reflux to form the ester. So some secondary alcohols can be identified by the iodoform test. We're going to get a yellow precipitate. More on this later when I discuss carbonyl. So all carbonyl carbons are sp2 hybridized. There are two types of carbonyl: aldehydes or ketones. Aldehyde is CHO and ketones are CO, R on both sides. How to produce them? So aldehydes are produced by oxidizing primary alcohols followed by distillation using K2Cr2O7 acidified or KMnO4 acidified. I'm showing you the reaction here. Ketones are produced by oxidizing secondary alcohols. So here we don't need distillation because that's the only product we're going to get. But to collect it, we do need to distill it, but we don't need to do it immediately. Okay. What is the characteristic reaction of carbonyl? They undergo nucleophilic addition reactions. Okay. So remember, the reagent is HCN and the catalyst is KCN or NaCN. What is the function of the catalyst? Basically, HCN cannot provide a strong enough nucleophile. So we use KCN or NaCN to provide the cyanide ion CN minus in great amounts, okay? Which gets regenerated at the end of the reaction. So what do we get at the end of this reaction? Hydroxynitriles are produced. Okay, hydroxynitriles. That's the class of the compound produced. So they also undergo reduction. Aldehydes get reduced in the presence of either LiAlH4 or NaBH4, right, to produce primary alcohols, and secondary alcohols get reduced using the same reagents. No heat required. Okay, you'll see that in the book NaBH4 requires heat, but in the mark scheme they don't mention that. So so ketones are reduced to secondary alcohols. So the test for carbonyl is using 2,4-dinitrophenylhydrazine 2,4-DNPH. This is a condensation reaction, as you can see. I have shown you here. They react with ethanol is reacting with 2,4-DNPH to form this orange precipitate, and one molecule of water is liberated. Okay. So what are the tests for aldehydes? Either the Tollens using the Tollens reagent or Fehling's reagent. Tollens reagent is a solution of ammoniacal silver nitrate. A positive result is a silver mirror. We need to warm the test tube containing Tollens reagent and the aldehyde or the sample. And for Fehling's reagent, this is basically Benedict solution. The copper 2 plus ion turns into Cu plus, and we get a brick red color of Cu2O, as seen in biology if a reducing sugar is present. We also need to warm the container here. So both of these are tests for aldehydes, not ketones. Okay, and the type of reaction is oxidation, as the aldehyde is oxidized to form a carboxylic acid, or to be honest, a salt. Since this solution is alkaline, the carboxylic acid further reacts with the alkali in the solution to form a salt. One important thing to note is that for A2, Methanoic acid also gives a positive result because HCOH, even though it's a carboxylic acid, it has a aldehyde group and it's easy to break. I taught you beforehand, right? Like it is oxidized in the presence of KMNO4 and K2CR207, in fact, to form with just KMNO4, right? KMNO4 to form CO2 and H2O. Okay, so moving on, we have a test for methyl ketones. It's called the iodoform test using aqueous alkaline iodine. The positive result is a yellow precipitate. In the book, they mention warming the test tube, but in the question paper, they don't mention warming. Okay, so you don't need to say that. The type of reaction is either oxidation or hydrolysis since the CH3 bond is broken. It has two steps. First, we halogenate the methyl group followed by hydrolysis. So, who gives the positive test for the iodoform test, right? So there are two exceptions, ethanol and ethanol, and all methyl ketones and some secondary alcohols which have a methyl group at one side. Okay, I've mentioned it here. This is a typical reaction for the iodoform test. We have butanone over here, 4 carbon ketone. It reacts with 3 molecules of iodine and 4 hydroxide ions to form this. Basically hydrolysis occurs, right, of the CH3 bond. We get CHI3 from there, and the ketone is actually oxidized to form a carboxylic acid, or the salt, basically, since the solution is alkaline. And some iodide ions and water molecules are liberated. So the next thing on our list is carboxylic acid, right? These are all sp2 hybridized carbons, 120 degrees. So how do we produce carboxylic acids? Either by oxidizing 1 degree alcohols or aldehydes using K2CR207 acidified or KMNO4 plus heat under reflux. So very few reactions require heat under reflux, basically oxidation of alcohols and esterification. In the other ones, you can just apply heat, it's going to be fine. Some nucleophilic substitution reactions do require heat under reflux, like preparing some, halogen from alcohols using HX, right? So you can also prepare them by hydrolyzing nitriles, acidic hydrolysis, H plus equals plus heat. This is what you need to write to get marks in the question paper to get carboxylic acid. The inorganic product is not important. You can also hydrolyze it using an alkali, but you need to acidify it later on. Okay, so it gives us the same thing. It's fine. You can also hydrolyze esters using H plus equals plus heat or alkali, then acidifying. You'll get the carboxylic acid. So a carboxylic acid is an acid, right? So it's going to react with metals to form a salt plus hydrogen gas. It's going to react with alkalis to form a salt plus water. It's going to react with carbonates to form salt plus water plus carbon dioxide. This is very important because alcohols do not react with sodium carbonate. So it's important for AS chemistry. Na2, you can differentiate between phenol and stuff because alcohols will react with sodium. So will carboxylic acids, right? But only carboxylic acids will react with sodium carbonate. Remember that, carbonates in general. So they also undergo esterification. They react with alcohols in the presence of a few drops of concentrated H2SO4 and heat under reflux to form esters. They can be reduced using LiLH4 only. We cannot use NaBH4 because it's not strong enough. This is the reaction. We're going to get an alcohol, primary alcohol. Okay, so esters, we can produce them by reacting alcohols and carboxylic acids and concentrate H2SO4 plus heat under reflux to give us the ester ethyl ethanoate. They can be hydrolyzed in two ways, either in acidic conditions or alkaline. Acidic hydrolysis of esters gives us carboxylic acid and alcohol. Alkaline hydrolysis gives us a salt and alcohol because the carboxylic acid reacts with the alkali to form a salt. So what about nitriles? We can produce nitriles in two ways, either nucleophilic substitution of halogenoalkanes using KCN, ethanolic KCN heat and the halogen alkane to form this nitrile, or using nucleophilic addition of carbonyl compounds. So this actually requires heat according to the syllabus. Although you won't see it in question paper at times, it actually requires heat. Okay, nucleophilic addition requires heat. So ethanol, um, for example, reacts with HCN, the reagent, in the presence of KCN catalyst and heat to produce hydroxynitriles. Why are these two reactions so important in organic chemistry? Because using them, we can increase the number of carbon atoms. Okay, so this is very important for drug synthesis. Okay. So for the next one, we can hydrolyze nitriles to form carboxylic acids. Alkaline hydrolysis also works, but you need to acidify it to get the carboxylic acid. And you can reduce nitriles using LiLH4 or hydrogen plus nickel or platinum catalyst to get amines. Okay. This isn't in the syllabus, but I'm still gonna say this because you're gonna find this in paper 1 at times. This is important for A2. So amides can be hydrolyzed in two ways. Acidic hydrolysis gives us the salt from the amine because the amine is basic due to the lone pair. It reacts with the acid to form the salt, and you're gonna get a carboxylic acid. And alkaline hydrolysis is gonna give us a salt because the acid reacts with the alkali to give us a salt and an amine. Okay, we're moving on to the last section of the video where I talk about mechanisms. We have 4 mechanisms in AS and 6 mechanisms in A2. In A2, we have electrophilic substitution and addition elimination. In AS, we have and in AS, we have free radical substitution, electrophilic addition, nucleophilic substitution, and nucleophilic addition. Okay, so starting with free radical substitution, this is typically a reaction of alkanes. Okay, um, so arrows are not required in this mechanism, but I saw it in the specimen 2022 paper for AS chemistry paper 2. So you can learn it. I'm going to show you. We have 3 steps: initiation, propagation, termination. In initiation, no free radicals are involved, but we do get 2. Due to the presence of UV light, the halogen breaks to form free radicals. In propagation, it actually occurs in multiple steps. We have 2 steps here. Methane actually reacts with the chlorine free radical to give us the CH3 free radical and HCl. Then the CH3 free radical reacts with chlorine again to give us chloromethane and the free radical. If you see this, the chlorine free radical has been regenerated at the end, right? So this is an example of catalysis. And the breakdown of the ozone layer also occurs by free radical substitution. That's why CFCs are bad. They deplete the ozone layer, okay? And in termination, so the 2 free radicals, always remember, in a termination reaction, 2 free radicals will react to form a product with no free radicals, okay? And you can show these arrows as I've shown here. I've seen this in the specimen paper, okay? Arrows can be shown here as well, but I don't think they're required. Okay, I saw this in the syllabus. They're saying that arrows are not required, so it's fine. So electrophilic addition is a characteristic reaction of alkenes. I've shown you 2 reactions here, one with a non-polar bromine molecule. When the bromine comes to close proximity to the electron-rich pi bond, the electron cloud is actually pushed away, so it becomes polar. A dipole is induced. So the attack is from the pi bond to the the arrow is from the pi bond to the electropositive bromine over here, and heterolytic fission occurs. So in the second step, we actually get a carbocation and the bromide anion. So the bromide anion will attack the carbon in the middle. So we actually had a possibility of the carbocation being formed at the end. The carbocation could also be formed here, but it's just that the one being formed at the middle is much more likely because it's forming a 2-degree carbocation, which is much more stable. So this is more common, part B. Here, the alkene is reacting with HBr. It already has an inherent dipole. Okay, so heterolytic fission is much more easier. So in the first step, we show the curly arrows. The attack occurs. And then in the second step, the nucleophile is going to attack the carbocation. So why is it called electrophilic substitution? Because the electrophile, right, H plus with a partial positive charge is actually substituting or it's attacking the alkene essentially. That's why it's called electrophilic addition. Okay, we are referring to the first step. So what about nucleophilic substitution? This is a bit more complex. Nucleophilic substitution is of 2 types, either SN1 or SN2. Let's talk about SN1 first. What is the why is it named SN1? Because rate of reaction actually depends on the concentration. Rate of reaction actually depends on the concentration of the halogenoalkane. Do you understand? So in SN1, it's a double step. It's a double step reaction. In a multi-step reaction, the slowest step is called the rate determining step. So what happens here? In the first step, there's heterolytic fission of the halogenalkane. We're gonna get a carbocation. This is the slow step, okay? And in the second step, the hydroxide actually attacks the carbocation, and we get the alcohol from the halogenalkane. This is called hydrolysis of halogenalkanes. So in A2, you're gonna get a question like this: if it was a chiral carbon, how many products would we get? Like, would we get only one isomer or both stereoisomers? We would actually get both because the hydroxide can attack from any direction, okay? But in SN2, hear me out, the hydroxide can only attack from one direction, okay? So we are only going to get one stereoisomer. Okay, so in SN2, why is it called SN2? The 2 refers to the number of molecules that rate depends on. Okay, 1 degree halogenoalkanes undergo SN2. So rate depends on both the concentration of the halogenoalkane as well as the hydroxide anion. So both things occur simultaneously. The hydroxide will attack. I've actually missed the dipole here. This is del plus and this is del minus. I missed it here as well. This is del minus and this is del plus. Okay. So the hydroxide actually attacks the electropositive carbon atom and heterolytic fission occurs. Then we get a hybrid compound, which has not been we have not been able to isolate this in the lab. It's purely hypothetical, which has a negative charge due to the hydroxide ion. So basically, these are dotted lines, right? What does this indicate? This bond is breaking and this one is being made. So both occur simultaneously, basically, right? And we get our final product. So since there's only one step in the reaction and both the halogenoalkane and hydroxide are taking part in it, rate actually depends on the concentration of both of them. What about the last mechanism? That's nucleophilic addition. It's for carbonyl compounds only. It requires heat. KCN is the catalyst. So in the first step, the CN from the catalyst, KCN or NaCN, actually attacks the electropositive carbon. It's attached to a electronegative oxygen, so a dipole is created. Okay, and heterolytic fission actually occurs of the pi bond. So in the second step, we actually get an O minus charge, and the CN is attached to the carbon now because the carbon could not have 5 bonds, right? That's why we sacrificed one bond. Now what happens? The O minus actually attacks an H plus. Where did we get this H plus from? The HCN reagent that we added in the first place. Heterolytic fission occurs in the HCN, which actually gives us this H plus. So O minus actually attacks that H plus, and we get our hydroxynitrile. And the interesting part is the CN that we used initially has been regenerated. That's why it's acting as a catalyst. Okay. And the last one, I've shown you the same reaction using ketone. Okay, we're getting a hydroxy nitrile here as well. Okay, so you can ask me any questions and drop a like and subscribe if you like the video. I'm gonna do the A2 chemistry one as soon as possible, and I'm gonna link it up here on the right, maybe here when it's up. All right, see ya.